Welcome back to my channel. We are going to continue with this hemodynamics talk, but do what you guys have been asking for a long time and is really just my least favorite thing, which is math. So the formula specifically for stenosis, and then we are going to talk about stenosis and regurgitation of the valves on the waveforms. Now there's definitely real life application, but obviously the monitoring system does a lot of this for you. So most of the actual math stuff you're going to have to do is either a ballpark what you're doing with your eyes if you don't snap it on the monitor, or on the RCIS exam, or maybe another boards exam you are taking. So we're going to start with really the most popular one, which is aortic stenosis. So in order to really understand the formulas, you have to understand a bit about the disease process itself to figure out what waveforms you need, where you're looking, when it's measuring. So aortic stenosis, what do you need to measure it? And we're talking invasive during a right heart cath, left heart cath, those sorts of things. Obviously, you can get some of these measurements on echo. That is not what we're talking about here. So you need a left ventricular waveform and an aortic waveform. And the reason is the aortic valve sits between the left ventricle and the aorta. So if this is a door and there's a problem with that door, you need to figure out what's before it and what's after it to see if there is a pressure resistance problem in that area, which is really what aortic stenosis is. Now you don't have to, but you should get a simultaneous pressure measurement with a dual lumen catheter like a Langston. Langston is just the brand name, but this is what it is. It looks just like a pigtail, except there's two transducers, distal and proximal. There's one for the left ventricle and then one for the aorta, depending on where it's positioned. So when it's positioned correctly, you should have both an LV and AO waveform. And the reason for this simultaneous pressure measurement is when it's the difference between a patient getting a TAVR or not, right? Something that important, you really want to be accurate. A lot can happen on a pullback, we'll talk about in a second, but this is really, per the board and kind of what you're looking for, the gold standard and most accurate way of measuring. So what is going on? In aortic stenosis, there is a pressure gradient. So that means a difference in pressures at a certain point in time when there shouldn't be. During systole, because during left ventricular systole, remember when we've talked about hemodynamics before, everything is in relation to the ventricles, right? Nothing else seems to be important. So during left ventricular systole, and that is when the aortic valve opens, and it lies again between the left ventricle and the aorta, which is why you need those two waveforms. Now, direction does matter because technically, if I just write this out really quick, let's say my LV systolic was 120 and my AO systolic was 220. Now, is there a pressure gradient? Yes, of 100 millimeters of mercury, but it's backwards. So let me explain what that means and why that's important. So LV, let's make LV 220, AO 120, okay, versus LV 120 and AO 220. This is what I mean when I say direction matters. So there's a gradient, a difference in pressure here of 100 millimeters of mercury. Left ventricular pressure is higher than the aortic pressure, right? So this pressure is higher, aortic pressure is lower. That coincides with aortic stenosis, because if there's a stenosis at the aortic valve, all of the pressure prior to that valve will be increased because it can't get through the door, and then everything after that will be lower because, again, it can't get through the door, so you're having kind of less volume there. Now, what about the other way around? If my LV pressure is 120, I'm sorry, I should have made this easier to read, and this wasn't really easier to read. No, it was that. Okay, this picture is not great. LV is 120 and my AO pressure is 220. Now, is stuff getting through the door? Yes, obviously, because the LV pressure is pretty normal, my AO pressure is high. There is a gradient, right? If you're not paying attention to direction, there is a 100 millimeter mercury gradient as well, but it's the opposite direction. So this is not an outflow problem from the left ventricle. That is not aortic stenosis. That could be sometimes regurg, sometimes aortic systemic hypertension, but it's not a diagnosis of aortic stenosis, which is very important for you to pay attention to if you're not paying attention to the direction of the gradient. Okay, remember this is what we talk about with hallmark signs. So hallmark sign is the pressure gradient between the LV and AO, with the LV being higher and the AO being lower during systole. You can also have diastolic issues, right? But that is not what we're using in this hallmark sign type of question. Now, what if I found a gradient on a pullback? So a pullback is if this was a normal pigtail, not a dual lumen pigtail, like you do for almost every case. If you dip into the LV to get LV EDP and you pull back, you do look for that systole, right? So like I'm in the LV, I pull back, I go into the aorta, and I'm looking to make sure there's no gradient between there. Versus if I pull back and my AO pressure has a difference, okay, ignore this one, that would be aortic stenosis. But this is why it can mean other things. So if you had a pullback, a gradient during pullback, that could be HOCM, hypertrophic obstructive cardiomyopathy, where you have hypertrophy usually of the septal wall here. So it's going to mimic aortic stenosis when I do this pullback. Coarctation of the aorta, so you could have an intra-aortic gradient, which might look like this as you're pulling back, and you go, that's weird, why did that change? It could have just changed because of your movement, right? But you can have coarctation of the aorta, stenosis or disease in the aorta. You could also have disease in the aortic root or arch from calcium, and that could cause a gradient as well. Will it be super significant? Probably not, again, unless it's coarctation or there's some sort of severe occlusion. But those are all the reasons that we don't love a pullback, to make the difference between whether someone goes to surgery or gets a TAVR valve. We want kind of the best way to eliminate any of those ulterior possibilities. Have I had a patient who was scheduled for a TAVR that actually had HOCM? Yes. Depending where you're taking your simultaneous pressure gradient, you could have that. They should have seen that on echo. Sometimes you're not totally going to see HOCM on an LV gram. There's a lot of support against an LV gram, but you want to use all of your information. So if a patient, for instance, on echo didn't have aortic stenosis and you're suddenly seeing a gradient interprocedurally, that should be a red flag. Why don't these things match up? That can happen with a lot of other valvular issues too. In regurg, you might need like a fluid challenge to see if they can handle some of that increased volume. Maybe they were just dry and dehydrated, so you weren't appreciating the stenosis or regurg. A lot of that can happen. So you want to use all your information, but if you're just talking about the board, you really want to have a simultaneous pressure measurement with something like a Langston for that reason, just because it's going to help it be more accurate in majority of cases. Where on the waveform are we going to look? And again, we're still talking about aortic stenosis here. And we said we're going to look, what two waveforms do we need? Left ventricular and aortic. So you need to know which one is which. Okay, you can go back to the basic hemodynamic waveform video if you need. But this one is the LV waveform. And then this one down here is the AO waveform. And then where are we going to look for the gradient? During systole. Now the question is, when is systole, right? LV systole. At the peaks. So the troughs at the bottom here, bottom of the AO, bottom of the LV, this is diastole. We look here for other things, but we're not going to look here for aortic stenosis. We're going to look up here in the difference between the systolic peaks. So let's see if we can measure. Now this is simultaneous. Both of these are overlapped, happening at the same time. Where is, oh, it's all the way over here. So I'm just choosing these. So this is, say, 180. And again, just trying to make this a little, man, that's really like 95. Whatever, we'll do 180. So you're going to do 180 minus 95. So that's LV systolic pressure minus AO systolic pressure. And you get, I'll write it here for you, 95, and that's millimeters of mercury. And that is 85 millimeters of mercury. Now, what type of gradient this is what we call a peak-to-peak gradient. You'll hear the word mean gradient. That is not what this is. That is on the printout as well. You'll have two different gradients for this one. But the one you're manually measuring here, where you measure LV systolic minus AO systolic pressure, because remember LV should be greater than the AO, that is your PP or peak-to-peak gradient. Okay. Now, how do you calculate a gradient? Because we have two formulas for aortic stenosis. We have, I've always called it Hakki, Hakki, and then Gorlin. Gorlin is the gold standard. It's more, if you look at it, it's more complicated, so you can think of that as more accurate, although I know that's not what that means, but just if you have trouble remembering. And Hakki is an estimate because you can only use peak to peak for Hakki, so you can do this with any pullback as long as you have a cardiac output calculated, or maybe you're doing a right and left heart cath, you have FIC calculated, you can use that. And what you're going to do is the aortic valve area equal to whatever the cardiac output is, and this is important. The difference between the two, cardiac output for Hakki uses liters per minute, and in the Gorlin it uses milliliters per minute. So let's just say it is 3 liters per minute over the square root of the peak to peak. So let's use the one we just got. All right, we got 85 millimeters of mercury. Now, my rule of thumb for math in general is to round out to 3 places when you have a decimal point until the very end, especially something like this where the difference between, 0.6, 0.4, and 0.8 can mean different grades of aortic stenosis. It's important that you really don't round until the very end because it can make a very big difference in the number that you get. So the square root of 85 is a long number, and make sure you're trying to do this with me as well. So you'll get 9.219554446. So let's use that. And then we'll do 3. And remember, on the exam, you're going to have a calculator on the computer. So it's important to probably use the calculator on your laptop or on your phone so that you're used to using that, not a regular calculator. So 3 divided by 9.2195 is, now this is a really intense number because that was a really intense gradient, 5397, right? So I would say 0.3, whether you round up or down, and that is in centimeters squared. That is the aortic valve area for Hakki. Now let's talk about the Gorlin formula. Now this has multiple steps, so you really want to write this one out. Cardiac output is in milliliters per minute, so remember you need to do a conversion. You need to multiply by that 1,000 that you see over here to change the liters to milliliters per minute, but you might be given milliliters per minute. Just pay attention. The SCP will be provided to you. There is a way to manually calculate it based off of the overlaid printout, but I think it's in West Todd, maybe an explanation on how to do that, but they will not require that of you. So what you're looking at with the Gorlin is when you get a printout of the overlaid simultaneous waveforms, it's going to look like this. So you do have the LV, the AO, but you do see the shaded area. So the systolic ejection period is utilizing really this entire area. Now it seems like it happens in an instant, but technically it does happen over a matter of seconds, and those seconds matter. And then the heart rate at the time that this was obtained, you're going to use a constant, 44.5 or 44.3. I always think it's funny how constants are supposed to be constant, but they're different depending on what resource you use. You're going to see this both in the mitral and the aortic Gorlin formula. Personally, I use 44.5 because it's used most consistently in reputable resources. And then the mean gradient. Now notice there's 2 types of gradients, right? There's the peak to peak that you manually calculated, and then the mean gradient that's going to be provided to you that's calculated during this simultaneous instance. You can get both. You can get a peak to peak off of this waveform, but the mean gradient will be provided. It kind of happens at a different time. Now let's try to calculate Gorlin. So let's take a look at what's provided. We have 2 different gradients, peak to peak and mean gradient. So which one are we using for Gorlin? The mean gradient. So I'm going to cross out peak to peak. SCP is provided, the systolic ejection period, which makes sense, right? Because aortic stenosis is measured during systole. That happens during systole. The cardiac output is 4.5 liters per minute. Do we use liters or milliliters for Gorlin? Milliliters. So we need to convert this. So you're going to do 4.5 times 1,000, which is 4,500 milliliters per minute. And yes, if you learned the placeholder way, you could just move it out 3 decimal places because there's 3 zeros if you learn that way, but if you didn't, that's okay. You can do the multiples, the multiplication, it doesn't matter. So we're going to change this to the 4,500 milliliters per minute, and then the heart rate is provided. Now when we're doing this, you see there's kind of multiple steps, right? There's parentheses within parentheses. So we're going to do the top portion first. we're going to take the cardiac output, and this is plug and play, which means you're going to plug in the numbers provided for each of the areas. So you want to make sure you've memorized this formula and you write it correctly, because that can make or break your answer. So 4,500 over SEP, make sure you're also trying to do this with me, times heart rate, which is 80. Now, if you've ever heard of AO flow or mitral valve flow, that is the numerator, the first top number of this. So when you calculate this top portion, technically you're calculating AO flow. If you've just seen that variance in this formula, that's what it is. And then 44.5 times the square root of, what was the mean gradient? 33. All right, so I'm going to do the top portion first. I'm just going to do this in a different color. So I'm going to do 4,500 over, and I do like to write all this out. So if you get a variance in a number compared to what is an answer choice, you can go through each of your steps and see if you just had a weird rounding thing or something like that. So 0.25 times 80 is 20, and 4,500 divided by 20 is 4,500 divided by 20 is 225. So that is your AO flow. And then you have the bottom portion. Let's do the square root of 33 first. That is 5.74456. Remember, I'm really a big rounder outer. Okay, and 44.5 times that is 255.633. So you're going to take your numerator and denominator, 225 divided by 255.633, and you will get a calculator with the board exam. It is a computer-based calculator, so if you are used to using calculator in your hand, please start doing this on your phone or on your computer so that you're used to typing in those numbers that way. It does have a scientific calculator, so you can do the square roots, but I do recommend just doing this step by step so that you don't miss something or type it in wrong. So that's 0.88 centimeter squared. So your normal aortic valve area is 3 to 4 centimeters squared. We are calculating these on a stenotic patient, so you're probably going to see something around 1.5 or less. Now, if you're getting something like 0.1, 0.06, that's probably not correct, so you want to check some of your rounding and numbers. If you're getting something really huge like 30, 200, 400, none of that is correct either, or again, you missed a conversion or used liters per minute instead of milliliters per minute. So it's good to know the normals or around what's normal. So you're looking for a number between probably 0.3 to 4 for normal, and really anything bigger than that, double digits or especially negative, you know that you did something wrong. So just go back and check your work. Now, mitral stenosis. We are going to use kind of the same concepts and steps. You really need to understand it when it's occurring to be able to measure it. Good news is the formulas aren't too terribly different, and we'll talk about that. So you need, where's the mitral valve? The mitral valve is between the left atrium and the left ventricle. So you're going to use a left ventricular waveform, and you're going to use pulmonary wedge pressure or left atrial waveform. We're probably not going to do a transeptal puncture to get to the left atrium to get an accurate pressure. So we're going to do an estimate based on the pulmonary wedge pressure waveform, which you can get during a right heart cath. So we're going to have 2 catheters in and 2 access points. We're going to have a left ventricular catheter on the arterial side, and we're going to have a swan or a pulmonary wedge catheter on the right side. And again, we're going to take a simultaneous pressure measurement using both of those. Now, where are you looking? You're going to find a pressure gradient during diastole. Remember, ventricular diastole, that is when that valve opens, and it's going to be between the left atrium and the left ventricle. You're not going to do a pullback here. You're going to stay in these 2 positions and just record overlaid waveforms during the entirety of that cardiac cycle. So let's take a look at what this looks like. Now, this is a little different. We're looking in diastole of 2 waveforms that have drastically different pressures, right? Your LV pressure is like 120/09, so that's usually on a 200 scale, so you can see the systolic peak. And then your pulmonary wedge pressure waveform is in the 10s, right? So that is going to be on a 25 millimeter mercury scale. Could you put this on a larger scale? Yes, just you want it on this smaller scale so that you can see the diastolic pressure really, really well, and it's not totally zoomed out where you can't see anything. The LV systolic peak is way off the screen here because this only goes up to about 50. So all the way up here is 200, but you really don't need LV systolic, right? That's not where we're looking. We're looking in diastole. The only thing it's really helpful for is checking if your LV waveform is properly zeroed in on scale. You do probably want to check that before you go down to this zoomed in approach. But if you aren't sure what's going on, you might miss, because these just look like lines on the screen, that there is actually an LV waveform here. So there's LV here, pulmonary wedge pressure down here, and you're looking in the LV diastole, which is down here, if there is a gradient or a difference in pressures in diastole. This has it shaded in for you, but on the board it might not be in real life. It's not going to be until you click to calculate a valve area, and then it'll kind of print that out for you. So that's where you're looking. Now, this is not something you can do peak to peak for. This is not something that you can sit here and really calculate an estimated gradient manually. You do need to snap it and get all of that information because it is just a little more difficult, and that's okay. So we're going to talk about how you're going to calculate it. All right, this should look oddly similar to the aortic valve area Gorlin formula. There's not a Hakki, there's not an estimate here. And you have, again, cardiac output in milliliters per minute. You're going to have DFP, diastolic filling period. So what was for the aortic valve? Systolic ejection period, because during systole, the LV ejects out the aortic valve. In diastole, the mitral valve opens to fill the ventricle, right? So it makes sense. It would have a different type of measurement, a diastolic filling period times heart rate. You calculate that, and that is also what? Mitral valve flow. And then in the denominator, you're going to have, again, a constant that is not really a constant, right? There's variance, 37.7 or 38 times the square root of the mean gradient, again, provided for you. So let's look at what we were given. We were given a mean gradient. We're given diastolic filling period in seconds per beat. We're given cardiac output, again, 4.5. We already did that math, so we know that's 4,500 milliliters per minute. And a heart rate of 80. So let's plug it in and see what we get. So we have a cardiac output of 4,500 over the diastolic filling period, which is 0.68 times what? The heart rate. So we're going to calculate that whole thing, and then we're going to divide it by a constant times the square root of mean gradient, which is 50. So same thing that we did before. Let's do the numerator first. 4,500 divided by, find out what 0.68 times 80 is. 54.4. So 4,500 divided by 54.4 is 82.70. Nope. See, that's where you make a mistake. 72058, so that's 6. And then we'll do the square root of 50. Okay, so that's your numerator. And we'll do 37.7 times the square root of 50, which is 7.071, technically 711. And we'll multiply that by 37.7 or 38, whatever you choose. And that is 266.5792. Now I did make up these numbers, but that's a very big difference. So let me just check my math real quick. Cardiac output's 4,500, 0.68 times 80 in the numerator is 54.4. 4,500 divided by 54.4 is 82.720588. So that was correct. So 82.7206, which is your mitral valve flow. This is what happens when you make up numbers. You might not really get something super accurate. divided by 266.5792 is, oh yeah, that's like wildly stenotic, but you know, that's why I got something weird and I said, you know what, let me go back and check my math and just make sure it is correct. For comparison here, normal mitral valve area is large. The mitral valve is larger than the aortic valve, so it's between 4 and 6. Stenotic warranting an intervention is less than 1.5. Less than 1 is like super, super severe. 0.3 is super tiny. That's probably not realistic, but again, I made up these numbers, but I did have that red flag and I went and checked my math. But I hope this just serves as an example to kind of help you work through. Now, mitral regurgitation is a little different. Most of what they're going to ask you, they're going to want you to look on the waveform. Now, these are different because I can actually evaluate if a patient has mitral regurgitation based off of the pressure list. This is just a hallmark sign or indication. Again, you want to overlap this with your echo results and those types of things and actually do some measurements and look at the waveform. But if I look at this, you need to know normals first, correct? You need to know 653 is normal. 10, 25, 18, really, this is high, right? RV 2504, that's normal. 25, 9, 15, 120, 80, 93, 120, 09. Everything else is normal. Again, I just really wanted a clear-cut example for you. The pulmonary wedge pressure, or left atrial V, is how much greater than the A wave? About 2 times greater than the A. This is a hallmark sign of mitral regurgitation. What is not mitral regurgitation is if my pulmonary wedge pressure waveform was 25, 25, 25. They're all severely elevated, but this is not a hallmark sign of regurg. The regurg is the difference between the V and the A, because you can think almost when you have regurg, it's backfilling a second time so that volume is almost counted twice. There's a lot more that goes into it, but that's just to help you remember. Now on the waveform, if I gave you this and I said, does this patient have mitral regurg? You could say yes. If I give you a waveform, you need to be able to say, does this patient have mitral regurg? Yes or no. So you have to be able to pick out a couple things. Number one, you need to know which one is the V wave, right, versus the A in order to see if the V is greater than the A, because there are times where the A is greater than the V, so you don't want to confuse those. So what you need is a surface lead EKG, which you have several here to choose from. These are 2 different patients. This one did indicate it for you, kind of, but if I said click on the V wave, you need to know this is PQRST, PQRST. We talked about this again in the basic waveforms PowerPoint if you need to go back. Now, personally, I draw lines down, if I can get them straight on here, whatever, from the P and the T, and then from the T to the next P, and I will try to line these up a little better. Some people use the R wave, which is fine, but sometimes you have variable R to R or PVCs, and it's not as easy. I like the P and the T because they're almost always there unless the patient has AFib. So between the P and the T is the A wave, like PAT, P-A-T. And then between the T and the next P is the V wave. Now, once you're comfortable finding one, you can march out every other as long as they're in some kind of sinus rhythm, that this is AV, 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 AV. So you could click on any of these and that would be the V wave. Now, is the V greater than the A? Yes. By how much? Let's draw out this scale. This is probably in 5s, right? 25, 30, 35, 40. Oh, no, it's not. What the heck? So if you marched out this scale, let's just use this to estimate the A and the V. This scale is in 2-point increments of 2.5, which is not super nice. So this is about 25, 27.5, I don't know, maybe 28. This is 27.5. This is 30, 32.5, and then let's do one more, 35. Okay, so the A is 28, and the V is 35, which is not double. It's about 7 millimeter mercury difference. Now visually, this does have peaked V waves, so they could use this as a mitral regurg example, and that is what it is. Or they might take away the scale just to get you to look at it and be like, oh yeah, that's significant. You never know what the examples that they're going to use on the board, but just in real life, make sure you actually calculate it out. Like this example, for instance, doesn't have a scale, so I can't really get a numerical value for these, so they could definitely use this example. And again, PRT. So I'm going to bring down my P, bring down my T. All right, so I know this one in between, this is the A and this is the V. So the V is definitely larger. You can march that out, A, V, A, V. That is much larger than the A, so you could call that mitral regurgitation. Just make sure you click on the appropriate V wave. Next up is tricuspid regurgitation, pretty much the exact same thing for mitral regurg, but on the other side. So if we look at our list of pressures, remember pulmonary wedge pressure represented left atrium, all these are normal, RV is normal, PA is normal, AO, and LV. 653 is normal for RA, so 20 is definitely double, more than double 6. So this patient has possibly tricuspid regurgitation. Now on the waveform, you're going to see the same thing where you need to identify the A wave, and the V wave will be peaked and elevated. Remember, elevating of both like this, of your A and your V, is not regurgitation. So I hope that helps. Please remember, we do have a platform now for EP. We are growing over there, taking all of your questions. So make sure to engage with us on Instagram and Facebook at Don't Miss the Hiss. We're also on LinkedIn. And of course, engage with us on Don't Miss a Beat on our YouTube, Instagram, Facebook, LinkedIn, wherever it is that you connect. We are always happy to get your questions. Make sure you like and don't forget to subscribe. Thank you so much, and I hope you have a great day.